Hey guys, Justin Modern Muscle here. This segment is going to be about how your EFI motor measures airflow coming into the engine. There are two major ways that you can measure airflow, two major operating systems, one being a MAF system, the other being speed density utilizing the MAP sensor. Now, in a MAF sensor system, you have a MAF sensor. This is a flow meter. This is a specific instrument that is in your engine to measure the airflow coming into your engine. This is always in your intake track, and there's a number of ways that MAF sensors work. On this particular GM style, there are heated resistors inside the sensor themselves, and depending on how much heat is drawn away from those resistors is the amount of airflow that is calculated. Now, this is important when we talk about tuning because your fueling is dictated by measured airflow. There are calculations and algorithms that occur to process and create or establish the correct amount of fueling per airflow. So when you're talking about fueling, you're really talking about measuring airflow. So when you're tuning, it's really important to get your MAF calibration right. Now in tuning, you will be able to manipulate the sensor's data to its perceived amount of airflow, and that's how we make our adjustments on a MAF system. The way that we can control fueling is with what's called a speed density system. Speed density system is a fuel table. It's a 3D fuel table that is based on RPM and load or manifold pressure. The way we measure manifold pressure is with a MAP sensor. Right here I'm holding a 3-bar MAP sensor. There are a number of MAP sensors available on the market. All of your naturally aspirated vehicles utilizing speed density will have what's called a 1-bar MAP sensor. 1 bar equals 1 atmospheric pressure. So the environment that we're in right now is at about 14.67 psi. So what this will measure, if it's a 1-bar MAP sensor, is anything from negative 14.7 psi, which is vacuum, to 0 vacuum, which is 14.7 absolute pressure. Now, when we're talking about boosted vehicles, when we're converting a naturally aspirated car to a boosted vehicle, you'll often hear about changing the MAP sensor out. Well, this is important because if we were to take a 2-bar MAP sensor, that'll allow us to meter pressure in the manifold up to 14.7 psi boost pressure. So 2-bar means 1 atmosphere plus boost pressure, which will be an additional atmosphere. You can utilize anywhere from a 1 to 5-bar MAP sensor. So a 3-bar MAP sensor will allow us to get up to about 29 pounds of boost. Now, when we're talking about tuning, we're going to manipulate the speed density table. There are cells, predictive cells for calculated airflow based on the signal that we receive from the MAP sensor and the RPM that the engine's operating at. Now there are some cases, especially in the GM LS1 world, where we're actually utilizing both sensors in a hybrid system. The vehicle will use a MAF sensor as well as a MAP sensor. Now, these PCMs actually have both tables for your MAF calibration and your speed density calibration. They're utilizing what's called a dynamic airflow environment. In these vehicles, the speed density portion is typically used for high transient conditions. So if you go from a high vacuum to a low vacuum state in a short amount of time, that's what we call a transient condition. Your predicted airflow will refer to the speed density first. Now, once the airflow stabilizes and becomes more steady state, that's when we move towards the MAF sensor, which is extremely accurate in either steady state or non-high transient conditions for fueling. What's important to know when it comes to tuning systems like that is it's important to dial in both aspects of fueling, not just one or the other, because they play off of each other. And to get the best performance, the best throttle response out of the vehicle, you have to tune the vehicle both for speed density alone as well as MAF sensor. So what we end up doing is disabling one or the other of the circuits to dial in both separately, and then when they come together, they're both dialed in perfectly. You get great throttle response and great performance out of your engine. So we went over two major ways to actually measure airflow going into the engine. Now, these are predicted airflows when we're talking about calibrating the MAF and calibrating the speed density system. So what happens when there are environmental changes or things within the engine that make this vary a little bit? Now, typically in a speed density or MAF system, more so in a speed density system, environmental factors like humidity, temperature, things of that nature will affect your predicted airflows. So on a cool day, you have a denser charge than on a warmer day. So that becomes really important. So how does your engine adjust? Now in a speed density system, you can actually tune what's called the intake air bias. And this will change the algorithm to actually adjust for your barometric pressure changes, your temperature changes, your humidity changes the best it can through the algorithms to keep consistent fueling. But even those aren't always enough to make the engine run exactly the way it should be. And that's where a closed loop control system and your O2 sensors come in. So if I've got a situation where I've got a predicted airflow on a certain day and then it cools off, or humidity changes or the barometric pressure changes, I've got a 3 to 4% discrepancy now between my expected airflow and actual airflow. Well, not a problem in a closed loop system. The narrowband oxygen sensors will actually make changes, and that's what we refer to by fuel trims. There are two kinds of fuel trims. There's long-term fuel trims and short-term fuel trims. Your short terms are the fuel trims that are fast reacting. So these are your instantaneous changes to maintain your target AFR. Long-term fuel trims are learned. So these don't happen instantaneously, but when you have a consistent short-term fuel trim, those will be learned in the long-term fuel trims. Now these are constantly working with your narrowband O2 sensors to create the perfect fueling environment in your engine. So you just heard me mention a closed loop control fuel system, and you're probably saying, what does that mean? A closed loop control system is a system in which takes feedback from sensors and makes live adjustments. So what we have is a sensor, either speed density or MAF, that we've got a predicted airflow. That airflow goes in, combustion happens, those gases go past your narrowband oxygen sensors. Now in a closed loop system, you're going to take the information that those narrowband oxygen sensors are giving you and make live fuel adjustments via the fuel trims. So we know what closed loop fueling does. What is open loop? Open loop is simply acting upon your basic fundamental fueling. There are no adjustments made, it's an open loop. So it will take the information that you have in your PCM, your calibration, and it will add the same amount of fuel for each condition every time. Those gases will go past the narrowband oxygen sensors, but in the case of an open loop system, the information is ignored. So there is no feedback, there's no live adjustment, and that's why we call it an open loop control system. So now that we know how we measure air and what the control systems are wanting to do in closed loop and open loop control systems, we can talk about the different PCMs and options that you have to actually control your EFI engine. Now, typically a lot of what we do is modify the factory PCMs. The factory PCMs typically all operate in the same fashion with a narrowband oxygen sensor. Narrowband oxygen sensors are great for part throttle fueling. They're very accurate at what's called stoichiometric, which is a perfect burn between air and fuel. But what they're not good at is wide open throttle fueling and power enrichment fueling, which is when you're putting out the power. So most, if not all, factory PCMs go into open loop mode in wide open throttle. So what that means is that's when the tuning and the dyno tuning become extremely important, because there is no feedback system to log, read, and look at while this is happening, and there's no live adjustments. So if I modify my engine to bring in more airflow in a speed density system, I need to accurately reproduce the predicted airflows in my PCM so that when I go wide open throttle, I have the correct fuel that I'm looking for. Now, If you're looking at standalone systems, which means we're taking out the factory PCM of a vehicle and we're introducing an aftermarket PCM. What these utilize is what's called a wideband sensor. These work completely different from a narrowband. This will give you an actual AFR reading. You can do closed loop control system fueling with a wideband. What these aftermarket systems allow you to do is have closed loop fueling in wide open throttle conditions. This is extremely valuable for race cars and highly modified vehicles, so that environmental changes and things that happen, we can actually adjust for them with the speed of a computer live as you're running down the track. So systems like the FAST system and Big Stuff 3, we like to utilize in our big power vehicles, big boost, or big nitro shot cars, because we have an added safety factor of the PCM monitoring what is going on during your run.